In the last lecture, we have discussed ultrafilters. A filter F on a non-empty set X is said to be an ultrafilter on X if it is not properly contained in any other filter on X. That is, there does not exist any filter on X which is strictly finer than filter F. Today, we are going to prove some theorems on ultrafilters. Now, the first theorem states that a collection F of subsets of a non-empty set X is an ultrafilter on X if the following two conditions are satisfied. First condition is F has the finite intersection property, and the second condition is for every subset A of X, either A belongs to F or complement of A belongs to F. Let us prove this theorem. Here, collection F has these two properties, that is, F has the finite intersection property, and for any subset A of X, either A belongs to F or complement of A belongs to F. Then we have to show that F is an ultrafilter on X. Since F has the finite intersection property, then we know that there exists a filter F dash containing F. Let F dash belongs to filter F dash. Then complement of F dash doesn't belong to filter F dash. Why? Because we know that phi doesn't belong to F dash, and so if F dash belongs to filter F dash, then F dash complement of F dash can't belong to F dash. And since F is contained in F dash, so complement of F dash doesn't belong to F also. Hence, by second condition, F dash belongs to F, because if complement of F dash doesn't belong to F, then condition 2 implies that F dash belongs to F. We have shown that if F dash belongs to filter F dash, then F dash belongs to collection F. Since F is contained in F dash, and now we have shown that F dash is contained in F, so we have the equality, that is F is equal to F dash. That means F is a filter on X, and if F is contained in F dash, then we get F is equal to F dash. That means there does not exist any filter on X which is strictly finer than F. Hence, we have shown that F is an ultrafilter on X. Now we have a corollary. A filter F on a non-empty set X is an ultrafilter if for every subset A of X, either A belongs to F or complement of A belongs to F. Here it is given that F is a filter, and if F has the second condition of above theorem, then we have to show that F is an ultrafilter on X. As F has the finite intersection property, we know that every filter has the finite intersection property, and so F has the finite intersection property. And second condition, it is given that second condition is also satisfied in F, and so by the above theorem we can say that F is an ultrafilter on X. Now the second theorem states that a filter F on a non-empty set X is an ultrafilter on X if and only if for any subsets A and B of X, A union B belongs to F implies that either A belongs to F or B belongs to F. Let us prove this theorem. Let F be an ultrafilter on X. Let A and B be subsets of X such that A union B belongs to F. Then we have to show that either A belongs to F or B belongs to F. If A is equal to phi, then A union B is equal to B, and so B belongs to F. That means condition is satisfied. And if B is equal to 5, then A union B is nothing but A, and so we get A belongs to F. So if A is equal to 5 or B is equal to 5, then there is nothing to prove. So we assume that neither A nor B is empty, and we have to show that either A belongs to F or B belongs to F. So we take its negation. So let, if possible, A doesn't belong to F and B doesn't belong to F. Now consider the following collection G containing all those subsets G of X for which G union A belongs to F. As B union A belongs to F, we assume that B union A belongs to F. So by definition of G, B belongs to G, and this implies that G is non-empty. We shall show that G is a filter on X is strictly finer than F. Now we show that G satisfies all the properties of a filter. So we check the first property as phi union A is equal to A, and we have assumed that A doesn't belong to F, and so by definition of G, phi doesn't belong to G. Now we check the second condition. Let G belongs to G and G is contained in H. Then by definition of G, G union A belongs to F. As G union A is contained in H union A and F is the filter on X, so F contains all supersets of its members. And since H union A is a superset of its member G union A, so H union A belongs to F. So by definition of G, H belongs to G. Now we have to check the third condition. Let G belongs to G and H belongs to G. Then by definition of G, G union A belongs to F and H union A belongs to F. And hence, their intersection is also in F because we know that F is closed under finite intersection. So G union A intersection H union A is equal to G intersection H union A belongs to F. So by definition of G, G intersection H belongs to G. So we have shown that G satisfies all the properties of a filter. So G is a filter on X. It remains to show that G contains F. So we take any member of F and show that that member belongs to G. Let F be an arbitrary member of F as F is contained in F union A. So F union A also belongs to F because F union A is the superset of its member F, and so F union A belongs to F, whereby by definition of G, F belongs to G. Hence, we have shown that any member of F is a member of G. Hence, we have shown that F is contained in G. Since B belongs to G and we have assumed that B doesn't belong to F, therefore G is strictly finer than F, which contradicts the hypothesis that F is an ultrafilter on X. So our assumption is wrong. We have assumed that neither A nor B belongs to F. Hence, either A belongs to F or B belongs to F. Conversely, that for any two subsets A and B of X, A union B belongs to F implies that A belongs to F or B belongs to F. We want to show that F is an ultrafilter on X. Let A be any subset of X. As F is an ultrafilter on X, then X belongs to F. Why? Because we know that filter contains supersets of each of its members. And since X is a superset of any member of F, so X always belongs to F. And X can be written as complement of A union A. And since X belongs to F, so complement of A union A belongs to F. By hypothesis, as we have assumed that A union B belongs to F implies that either A belongs to F or B belongs to F. So either A belongs to F or complement of A belongs to F. But we know that a filter on set X is an ultrafilter on X if for any subset A of X, either A or complement of A belongs to the filter. And so here this condition is satisfied. So we can say that F is an ultrafilter on X. Thank you.